Assalamualaikum warahmatullahi wabarakatuh and very good day I wish to everyone. My name is Nur Shazana Bitesa and today's presentation will provide insights into synthesis, characterization and antibacterial properties of Thiourea Ligands and their copper and nickel complexes, which equipping you with the knowledge to understand their potential as new antibacterial agents. The detailed slides will guide you through each steps of the research process. This work was supervised by Associate Professor Dr. Karimah Kasim. Now let's walk through it. To begin, let's look at the background of this research. The motivation for my research stems from the increasing resistance of bacteria to existing antibiotics, which is a major global health concern. Thiourea compounds and organosulfur, which is known for their wide applications in organic synthesis and pharmaceuticals, which have shown potential as antibacterial agents. The presence of metallic ions in these compounds can enhance their microbial potency, making them effective against various types of bacteria. Now, let's move on to the problem statement. The rise in antibiotic-resistant pathogens in both human and veterinary medicine is alarming. Unfortunately, the development of new antibiotics has significantly declined. This calls for alternative approaches to combat with bacterial infection, which is the focus of my research. Next, we will discuss the significance of this study. This study aims to develop a new series of antibacterial agents to address the challenges posed by antibiotic-resistant bacteria. The successful development of such agents could lead to innovative antibacterial drugs, thereby benefiting public health by combating infectious diseases. Let's proceed to the objectives of the research. The main objectives of my research are: first, to synthesize and characterize benzoyl Thiourea ligands and their metal complexes copper and nickel. Second, to screen the antibacterial properties of these synthesized compounds using the Disk diffusion method on both gram-positive and gram-negative bacteria. And lastly, to analyze the biological properties of the ligands and their metal complexes using computational methods, specifically density functional theory (DFT). Now we will review some relevant literature. The literature review covered key studies that provided the foundation for my research. For instance, previous work guided me in selecting the appropriate methods for synthesizing the ligands and metal complexes. It provided insight into using the condensation reaction with specific ratios of benzoyl chloride and potassium thiocyanate with an amine for ligand synthesis, as well as the precise ratios of ligands and metal salts required for the formation of metal complexes. As for characterization, the synthesized compounds were carried out using various spectroscopy techniques as shown in Table 2, where each technique has an important peak that serves as my references, where C double bond S at around 1200 cm1 for FTIR spectroscopy and H at range of 8 to 10 ppm, and for UV visible spectroscopy, C double bond S and 2 pi star might be observed at around 270 nanometer. Moving on, let's look at the methodology. It involved 3 important steps, including synthesizing the ligands and their metal complexes, characterizing the compounds using different spectroscopy technique, FTIR, proton NMR, UV visible spectroscopy, and computational studies (DFT). And the last methods were evaluating the antibacterial activity of the synthesized compounds using the Disk diffusion method against both gram-positive and gram-negative bacteria. As shown in the pathway figure, the synthesis of the ligands involved a condensation reaction in a 1:1 ratio using acetone as solvent and being refluxes for total 2 hours and 30 minutes. While for the metal complexes, they were formed by reacting the synthesis ligands with metal salts in a 2:1 ratio, which being refluxed under room temperature. The ligands were dissolved in dichloromethane and metal salts in ethanol solvents. The synthesis was optimized based on the literature methods to achieve high yields and purity. This method was done for all 3 ligands and their metal complexes. Next, let's discuss the results and their characteristics under different analyses. Let's begin by discussing elemental analysis, chemical and physical properties. As shown in Table 2, the results showed that experimental values were in good agreement with the theoretical values, confirming the high purity and correct molecular formula of the synthesis compound, while in Table 3 indicated the other properties of the compound such as color, matter, and its solubility in DMSO, acetonitrile, and water. The compound exhibited melting points below 130 degrees Celsius and the synthesis process is achieved yields greater than 50%. In melting point analysis, the synthesis metal complexes showed higher melting point compared to the ligands due to the presence of new ionic bond and dative bond, which significantly strong bonds that produce a larger size of compounds. Next, we will look at the FTIR spectroscopy results. Infrared spectra of synthesized compounds were recorded at 4000 to 450 cm1 as KBR palette, where we focus on the important pin corresponding to the C-double-bond-S group of ligand 1 and its metal complexes. Notably, there was a shift in the C-double-bond-S stretching frequency upon coordination with the metal from 1100 to 1092 and 1164 cm1, indicating successful complex formation. Moving on, let's examine the UV-visible spectroscopy data. It showed distinct electronic transition which confirmed the complex formation. The UV-visible spectra also revealed the observed peak in acetonitrile solvent corresponding to the pi-to-pi star electronic transition of the C-double-bond-C bond of the benzene ring. Bethochromic shift or redshift were observed in the formation of complex from its ligand where it shifted to higher wavelength. In contrast, due to its polar nature, DMSO revealed an absorption band at 271 nanometer attributed to the N to pi star electronic transition of the C-double-bond-S group, indicating solvent-dependent variations in the electronic transitions. DMSO probably enhanced the solvation of polar functional groups in thiourea ligands and their metal complexes compared to acetonitrile. Now, let's discuss the proton NMR spectroscopy findings. The compounds were prepared in deuterated solvent DMSO with 10 to 50 mg of the compounds we used to dissolve. Based on L2 and L2Ni spectrum, the aromatic hydrogen atoms attached to a chlorine substituent appear more downfield, showing higher chemical shifts compared to the aromatic hydrogen atoms without any substituent. This is because CH3 was known to be electron donating group and gave shielded effect to the compound. Additionally, important peaks such as NH proton was observed at around 8 to 10 ppm due to the deshielded effect where their signals appeared at higher chemical shift value which confirmed the presence of the amine group for both ligand and metal complexes. Next, we will analyze the computational study results. It was performed using the Bitrilib functional combined with the Line L2 DZ basis set in the Gaussian 09 software package for investigating the electronic structure, molecular geometry and properties of thiourea compounds from the frontier molecular orbital NGs. Molecular orbitals also can be visualized as shown in figure above, HOMO and LUMO, to understand the bonding interactions within the molecule. DFT calculation also revealed the electronic structure and stability which supports the experimental results. The calculation indicated that L3 with two different behavior for alpha and beta spin, showing an extremely small gap compared to other ligands. However, the smaller the band gap suggesting it might have the greater antibacterial properties compared to L1 and L2 that might show potential but might be slightly less than L3. Lastly, let's review the antibacterial analysis. Table 5 showed that most of the compounds have antibacterial effects against 2 gram-positive bacteria, MRSA and S mutants, and 1 gram-negative bacteria, TDB35, with triplicate analysis. Solutions of the synthesized compounds were prepared in DMSO at a concentration of 5 microgram over milliliter. As DFT calculation suggested, L3 would have the highest inhibition due to its small band gap, yet L1 and L2 exhibited better inhibition. According to a study, the discrepancies between DFT predictions and actual antibacterial performance can arise from factors like solubility, permeability, and actual interaction with bacterial cells, which might not be fully represented in the theoretical model. The results also showed that the metal complexes were more effective than the ligands, which can be explained by chelation theory. When the ligands form complexes with metal ions, they become more stable and can penetrate bacterial cells more easily. This increased the stability and permeability makes the metal complexes more effective at killing the bacteria. To conclude, the thiourea ligands and the copper and nickel complexes were successfully synthesized and characterized. The ligands were synthesized by reacting benzoyl chloride, potassium thiocyanate, and amine in a 1:1 ratio. For the metal complexes, a 2:1 ratio of ligands to metal salts were used. Both acetonitrile and DMSO were used to prepare the Thiourea Ligands and their metal complexes to enhance the solvation of specific functional groups like the C double bond S. Future research could explore synthesizing other metal complexes with Thiourea ligands, investigate their mechanism of action against bacteria, and also test their effectiveness against a broader range of bacterial strains. Thank you for your attention for taking the time to review my research. I appreciate the opportunity to present my work to such a distinguished panel of examiners. Your constructive feedback and thoughtful questions will be incredibly beneficial.